Diamond, one of the strongest and rarest gemstones on the planet, forms from graphite through billions of years of extreme heat and pressure. Michael wants to buy a diamond ring as he is getting married soon. He knows that a diamond is forever, but also worries that nothing lasts forever. So what's true and what's not? Luckily, Michael is a scientist, so he decides to find out the answer. Fundamentally, diamond and graphite are both made of carbon, but structured differently. We can write the formation of a diamond as a chemical reaction. What if we reverse the reaction? Do diamonds convert back to graphite? If so, under what conditions? To explain this, let's take a look at thermodynamics. There are two types of chemical reactions: endothermic, in which energy is absorbed, and exothermic, in which energy is released. An example of exothermic reactions is explosions. These reactions require an input of energy to initiate, but have an overall decrease in energy as more energy is released than absorbed. Endothermic reactions are the opposite. More energy is absorbed than released. They cannot occur without an outside source of energy. One example is boiling water. Heat is required to convert liquid water into steam. The formation of diamond is an endothermic process, as heat and pressure is required to change the structure of graphite to diamond. From this, we can already infer that the reverse, converting diamonds back to graphite, is an exothermic process. But let's take a look at the numbers. The change in energy of a reaction is called enthalpy. In an exothermic reaction, enthalpy is negative. The reverse reaction would be endothermic, with the same enthalpy magnitude, but positive. In nature, exothermic reactions tend to be favored. To calculate the enthalpy of a reaction, we can use this equation. We can plug these numbers in to get negative 1.88, the enthalpy for the conversion of diamond to graphite. This indicates that the reaction is thermodynamically favorable and will occur, as it is exothermic. But enthalpy isn't the only concept involved in determining whether a reaction is favorable or not. Another factor is entropy, or the measurement of the amount of disorder in a system. Let's pretend you're measuring the entropy of a room. If you don't clean your room, entropy will increase over time because it gets messier and more disordered. To calculate the entropy change of a reaction, we can use this equation. We get positive 3.26, which means that the conversion of diamond to graphite has an increase in entropy. Positive entropy is favorable in nature, so again, the reaction will occur. Since the conversion of diamond to graphite is both exothermic and increases in entropy, it will always be favorable. Then why don't we see diamonds spontaneously turn into black powder? Diamonds are metastable, which means they convert back to graphite with a sufficient amount of energy. Activation energy, the energy required to initiate a reaction, is needed for this process to occur. In 2017, scientists were able to use a high-energy X-ray laser to trigger this reaction, successfully converting diamonds to graphite. Now Michael can answer his question. Although the reaction is favorable in all conditions, it still requires an outside energy source to start the reaction, so luckily, we don't have to worry about these precious stones disintegrating into powder, unless it somehow gets hit by an X-ray laser.